All right, so we've done all our fluid pipe flow problems, but there's some more things about a piping system that you could encounter. The first thing that you could encounter is something that involves more than one piece of pipe, right? And so far what we discussed is only sections of pipe, just a system that involves one section. And we could have systems that involve several of those sections either in parallel or in series or in some combinations. And so the simplest possible case is some pipe sections in parallel. And for this we use the electrical circuit analogy. Of course, again, if you're doing this very often in your work, you would have some sort of computer program, but this is conceptually what one could do. And if you recall, Ohm's law can be written as E equals IR, where this represents a balance between a voltage E the current I and resistance R. So what we do is consider a fluid circuit by analogy, and which in a circuit you would have, in a fluid circuit you would have a balance between a pressure difference driving the flow, so analogous to the voltage which drives the current. We have a flow rate, so this is delta P. The flow rate would be Q, or the velocity V, analogous to the current, and flow resistance, that is our friction. Or perhaps we could add some sort of, as we're going to see a little later, we could have, in addition to the friction factor, some additional losses because of pipe fittings or other devices in the system. You could have valves and so on. So for the, if you recall our equation for the pressure drop, in terms of the friction factor, it was F times L over D times rho V squared over 2. So this is in terms of pressure drop rather than head loss. So write this as delta P equals to a Q squared times some resistance, let's call it R wiggle, where R wiggle is some sort of measure of the resistance to the flow. And that is, of course, proportional to F, the friction factor. And you can, with this, if you recall your different laws for the Ohm's law in systems, then you can apply the same thing with this analogy. I'm going to, let me see, where's the little picture here? Okay, maybe I'll just erase these things from here. You've got it all. And now I got my picture. Ooh, but look what happens. Oh no. That doesn't work, does it? Okay, we'll have to do it that way. Okay, so this case is pipes in series, and we would consider then that, of course, in a system of pipes in series, whatever flow goes through one pipe is going to have to go, conservation of mass, through every other section of pipes. So Q1 equals to Q2 equals to Q3, obviously, right? Continuity, basically. But with the head loss add up. So the total head loss is head loss in 1 plus head loss in 2 plus head loss in 3. So if Q is given, really this is a type 1 problem, and this is straightforward. This is the same as you just do a section of pipe at a time with the Moody chart, and it's straightforward to determine the losses, and in the end we just add them up. If instead, yes.
So these are pipes in series.
These are pipes in series, yes. By the electrical analogy, pipes in series and all of the losses add up. Like the resistances would add up in the electrical circuit, right? It should make sense to you that if I have a certain amount of resistance in one pipe and I add to the end another piece of pipe, those losses will add up, right? And any pump driving the flow will have to overcome the additive resistance of all those sections of pipe in series. But I've expressed things here in terms of the head loss, and the equation I wrote before was in terms of pressure drops. So you can use either one, but not mix them because they're different units. But they express it, so head loss or pressure drop express the same thing, but in different dimensions, right? The head loss is using a dimension of length to express how much pressure drop, equivalent pressure drop is happening. They express the same thing conceptually or physically. It's the same, is the resistance, yeah, yes. But you can mix those two things in an equation. And for the system in parallel, we have now to consider that the total flow rate in this case has to be the sum of the separate flow rates, right? In all the separate sections of pipe. Does that make sense? If we're moving things from one big tank to another big tank and they're connected in 3 different places, the total transfer of material from one to the other is going to be the sum of the flow rates of, in this case, we've got 3 pipes. So Q is equal to Q1 plus Q2 plus Q3, unlike the previous case, which had Q1 equal to Q2 equal to Q3 because they were in series. Here they are additive. Now, if we were to apply the energy equation from point A to point B, here and here, you would see that no matter which pipe a fluid uses, the head loss would have to be the same because these 2 points from A to B have the same elevation, same pressure, same velocity. And so the head loss has to be the same no matter which route I choose. I hope this makes sense to you that in this case, the head loss 1 has to be equal head loss 2 equal to head loss 3. Do you agree? By energy considerations? Okay, good. So this is analogous to an electrical circuit in parallel now. Oh, sorry, in parallel. That's what I meant. So we have, this situation, right, where we had R1, R2, R3 in the electrical circuit, and you have V1 equal to V2 equal to V3, and your total current is equal to 1 over R1 plus 1 over R2 plus 1 over R3 times V. Now, these are pretty straightforward. Then what you would have is also a system that's a little bit more complicated. Perhaps it has some branching happening. So that would be something like that. We call it a loop system. In that case, conservation of mass indicates that, of course, the flow rate through pipe 1 has to be equal to the sum of the flow rates in 2 and 3. So Q1 equal here to Q2 plus Q3 by conservation of mass. And if we were to apply the energy equation, like I hinted at in the previous case between A and B, you see that again we have same pressure, velocity A equals velocity B equals 0. But I don't know whether they're the same elevation. In this situation, we could have, tanks in different locations, water tanks or so on. So we apply the energy equation and we say, okay, Z, the elevation in A, because everything else is 0, pressure and velocity terms, equals to the elevation in B plus the head loss through section 1 plus the head loss through section 2 if the fluid goes in this path, or if the fluid goes in the other path, ZA equal to ZB plus HL1 plus HL2 if the fluid goes through the other path. Oh yes, thank you. Three. Well, we get that HL2 has to be equal to HL3 regardless of the difference in diameters. And so the flow rate has to adjust accordingly. You can see how this can start getting complicated if you have a big system, right? And so that's why there are computer programs to solve these things. In engineering firms, they would have But conceptually, we can see that it's possible. However, if you have 3 reservoirs in this sense, then it's not so obvious that you can solve this and even if all pipe properties are known, in this case what we have is some valves, okay? So this is a valve here in 1, 2, and 3, and so suppose that valve 1 is closed. So if valve 1 is closed, this is easy because flow is going to be from tank 1, sorry, B, to C, the one that's lower, right? If valve 1 is closed, yes, closed, then flow is from tank B to tank C. And then you can calculate the flow rates. But with all the valves open, the question is the flow out of tank A, the higher tank, that's going to be clear, it's going to be out of tank A, but is it going in B or is it going out of B? We can't really tell, right? So the direction of the flow is not obvious. And if you don't know the direction of the flow, you can hardly write an energy equation, right? So it gets a little bit more complicated. This depends on already many factors. So all valves open. The flow is out of A, tank A, because it's the highest one. That's clear. But is it out or into tank B? It's not obvious, and it's going to depend on many factors. I just want to point out that this now gets a little bit more complicated. We won't go into it, but just for your, if you're interested, if you're curious, you can look it up in some books. If you don't know the direction of flow unknown, then we can't easily apply energy equation and so on. You don't know which, and delta P's and so on. You don't know which point in the system is in higher pressure than the other one. And so similarly, if you have systems of pipes, they can actually behave in very unexpected ways. If you have a system, a complicated system of piping in, say, a city with valves all over the place, different elevations, and they can be, city water distribution systems can be very complicated, and basically the only way to solve these things are with some computer simulation programs. The way they would have done it before they had computer simulation programs would be trial and error. Try some things, calculate them out, see if it works. This would have been quite cumbersome before the age of computers, you can imagine. Oh, that's the case. Pipe flow, general pipe flow in systems, very difficult. Okay? So let's now discuss another aspect of piping systems before we got a few more minutes before we leave today. And this is with the situation that happens when you have fittings, we call them. Fittings would be the different sort of like bends or contractions or all sorts of different things that can be a part of a system. We talked about valves in a moment. This is just a moment ago. This is the typical valve in a water distribution system. The purpose of a valve is, of course, to regulate the flow. And with the valve completely closed, there's no flow. With the valve partially open, you would have some resistance to the flow, which is what you want to precisely accomplish. Regulate the flow rate by changing the resistance using this device. So because of the definition of how these things work, the losses in the valve can be quite significant because their purpose is to regulate the flow. Through applying a resistance, right? A resistance to the flow. If the valve is completely closed, then there's no flow. But with the valve partially open, there is some resistance, and this can be quite significant. Of course, you can see here that the geometry of the pipe is quite complicated, and due to the complicated geometrical features of this, it would be quite difficult to have any sort of analytical result or you know, to estimate the loss here. It's impossible, really. So the head loss for these pipes are always given through experimental data and are provided in spec sheets by the manufacturers. And the way that this is expressed is in terms of what's called the loss coefficient. So often we use KL, loss coefficient, and usually what one does is, let's see, I'm going to go up and chaotically write in all my white space that I've left here. I hope you can follow. So the loss coefficient is expressed usually in a non-dimensional way as the head loss. We usually call them minor losses, the major losses being the losses in the pipe section, as we've discussed in the previous part. So this is the minor loss of all the little fittings and devices in the system, and we non-dimensionalize that by the dynamic pressure, so V squared over 2G. The dynamic pressure, if I write it in terms of pressure, but here is in terms of head loss. In terms of pressure, it would be delta P over 1/2 rho V squared. So I'm going to clear up and write that again. HL minor divided by V squared over 2G equal to delta P over 1/2 rho V squared, dynamic pressure. And so we write HL. We're normally going to use our energy equation in terms of fluid head. So we want the head loss equals to KL, where this is the loss coefficient, as I said, provided by the manufacturers, and so available to us from mechanical engineering handbooks or spec sheets, times V squared over 2G. So for a given value of the loss coefficient, we can get the head loss for our specific design conditions by multiplying by V squared over 2G. So it depends on, the actual head loss is going to depend on the velocity. So the same valve depending on what situation you put it in your system, will result in more head loss for more velocity, less head loss for less velocity, right? So for a given loss coefficient, the actual head loss is proportional to the square of the velocity. And if you want to calculate things in terms of delta P, you can also write it in terms of the loss coefficient as KL times 1/2 rho V squared. It also depends on the square of the velocity. Now, the value of this loss coefficient K depends strongly on the geometry and many things, many other things. It's a function of geometry and Reynolds number and many other things. Who knows? But many times other dependencies are pretty negligible, and what's most important is the geometry, and they are obtained experimentally. And provided through spec sheets. All of these things are quite standard right now, the designs of valves and so on, and so you can always get them from manuals. Another way that one can work with these minor losses is, oh wait, a couple of people are still writing, so I'm going to, yeah, okay, good. Another way to work with minor losses is to use what's called the equivalent length, which is, well, as it says, an equivalent length of pipe that produces the same loss. And so many times this is useful. This equivalent length, which is the equivalent length of pipe that would produce the same loss. So for example, head loss minor expressed in terms of the loss coefficient would be KL V squared over 2G. And this is, and remember our head loss for the case of the straight sectional pipe was F times L over D times V squared over 2G. And so call this the equivalent length of pipe that produces the same head loss, and then you can solve for that length equivalent in terms of KL, and it's simply KL times D divided by F. So it's based on the pipe that you're using, of course. Because that determines both D and F, the pipe and also the conditions, operating conditions. So in this terminology, the head loss of a system, a complicated system, would be the sum of the straight sections of pipe and all of the components, any additional components that you may have. Valves is one, but there's several others. We're going to see now a quick list of the other sorts of sections, components that you may have. these components such as valves and other things. What other things? You could have I'm going to list them now. I'm just waiting for some people to finish writing. Okay. Entrances. Picture here of an entrance. When you have some entrance into a pipe, there's always going to be some sort of separation, little, you have little eddies that form there in the section, and then the fluid down the pipe sort of settles down and becomes fully developed, we call it. So there are different sorts of entrances that one could have when the fluid exits from a reservoir into a pipe system. The loss here is indicated in this pressure drop here is indicated in this graph, approximately what it would look like. In the ideal case, you would recover all the kinetic energy after the entrance, but in the real case, there's a loss that you can't recover from, and that loss is expressed again in terms of a loss coefficient multiplied by the dynamic pressure. And so what you can have is different types of entrances that are going to have a different value of this K. The loss coefficient depends on the geometry, like in the case of the valve. So what do we have? The possibility of I thought I had some pictures of the different types that you could have, but I guess I forgot to put that one in because this is exits. So let me just list them here, what the types of that you could have. You could have a sharp edge, and this gives you a KL of approximately 0.5. You can estimate that. Slightly rounded. Then you can get, all of these things are usually available in the engineering handbooks. KL is equal to 0.2. Obviously, if the loss coefficient is smaller, it's because the device is, is more efficient, it's less lossy. A well-rounded pipe, entrance will have a very low loss coefficient. Other sorts of devices that we could have, I was going to explain this, but I don't think it's necessary that we're going to all the details of explaining the vena contracta and sort of justifying the loss coefficient of 0.5. We can actually argue here and justify it, but let's move on in the interest of time to some other types of fittings. Exits are the other types of fittings that you could have. A pipe here, so the flow in this case is going in that direction, so from the pipe into a tank, and then you can have also rounded or sharp or some sort of slanted versions, and there's also a loss when a fluid enters a tank. Basically, the entire energy of the fluid is dissipated because from a velocity which is greater than 0, it goes to 0 inside there. So really, exit here is velocity different than 0 in the pipe, velocity equal to 0 in the tank, and so basically all the energy is lost, and so the KL is equal to 1 in this case, regardless of shape. Then what other things we have? We have changes in pipe diameters that are inside the, so going from a larger pipe to a smaller pipe or the other way around. And in that case, we talk about things that are loss coefficients that depend on the area ratio. And there's some relationship here that we can obtain for the loss coefficient. Here KL is in this plot a function of the change of area. So let me explain this in the, let's see, the next slide has this. No, it doesn't. Okay, so basically you can do a control volume analysis of the situation here, and you can look at the pipe expansion and do a control volume analysis, say here. The pipe continues, but I've got my control volume. Like that, and I can consider a section 1 here, a section 2, and a section 3, and assume the flow is uniform, and do mass, momentum, and energy. So mass, conservation of mass would be that A1 V1 is equal to A3 V3. What comes in must go out. The conservation of momentum is P1 A1 minus P3. So this is the only area where there's any flow, in this case, the area 1, because the rest of the control surface here and there doesn't, there's no fluid passing through that, right? So it's P1 A1, P3 A3 equal to rho A3 V3 times V3 minus V1. I'm just going to speed through this one because we only have a couple more minutes and you need to go to your next class. And energy, P1 over gamma plus V1 squared over 2 equals P3 over gamma plus V3 squared over 2. Am I forgetting a G? Yes, G plus head loss. This is the energy equation. And working with this, you can, working like this, you can, this gives KL equals to, this is the definition, and it's equal to 1 minus A1 over A2 squared. So you can get the actual expression for the head loss in this case when you apply mass and momentum and energy to the situation, and that's what's plotted in this. So this is a result, experimental, theoretical result, and in fact it has been confirmed to agree quite well with experiments. That's for sudden expansions and sudden contractions. Okay, now there's a couple more types of fittings, and we can discuss them briefly next class. Just a couple more, but we're almost done with this one. All right, thanks.